Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X and the Electron as the Primary Carrier of Gravitational Energy. Now, the evidence that the Planet X system of stellar cores is here in the solar system and is affecting both the Sun and the Earth is overwhelming and has been the subject of a great many of my articles. Through observing the interactions between these objects and the Sun, it has become clear to me that they are depleted in both energy and electrons. In addition, they absorb energy in the form of photons. And you may look at article 183 entitled Stellar Cores Absorb Photons which Carry Gravitational Energy for more details. And here is a composite SDO image from December 25th, 2017 showing a Planet X object or stellar core in the Sun's corona. And this object is obviously a solid spherical object. It is striped. The stripes are curved, and which we would expect for stripes on a spherical object. The stripes would naturally follow the contours, the spherical contours of the object. So this is a striped object in the Sun's corona. It is about 4 times larger than the Earth. Now, observations of these objects has led me to propose a new theory for gravity called electrogravity, which incorporates the electrostatic interaction. According to this theory, photons are the source of all matter and energy in the universe and can exist both as free particles and as photon energy inside of particles. I also call this photon energy gravitational energy because it is associated to the strength of the gravitational interaction between particles. Particles, that is protons and electrons, emerge from within a photon when it has sufficient energy, that is over 940 MeV, and it moves through a region of high enough electric field. Most of the photon energy goes into giving the two particles mass, and the remaining energy continues to exist as photon energy within the particles. And this is illustrated here. We see a photon, we see the proton and the electron within the photon, and these particles emerge from within the photon when it moves through a region of very high electric field, at which time most of the energy from the photon turns into the mass of the particles, and the rest continues to exist as photon energy within the particles. But this is actually photons existing within the particles. Now, the photon energy is divided equally between each proton and electron pair. So that is the photon energy that's now within the particles. And this occurs according to the equal energy sharing principle, which causes two particles to share energy so that both end up with the same amount of energy whenever they come into close contact with each other. And you may look at article 260 entitled Planet X in the Solar System, the principle of equal energy sharing for more details. Stellar cores are depleted in electrons and seem to thus operate as superions and will thus be electrostatically attracted to the Sun. You may look at article 184 entitled Stellar Core Evolution for more details on that. Thus, the electrostatic attraction seems to be what brings them to the Sun's corona. However, once there, they will be repelled by the Sun's positive core and will thus not collide with the Sun. Furthermore, they will absorb matter from the Sun, electrons first, as they touch the Sun's outer electron layer, and then ions. Once they have collected a certain amount of ions, though, the gravitational repulsion between electrons in the sun's corona, and the ions moving through the plasma connection toward the object eventually becomes much stronger, resulting in the object and a large amount of coronal plasma being ejected. In other words, the mechanism through which they draw matter from the sun leads to a CME, or coronal mass ejection, at which time the stellar core is ejected with the coronal plasma. And the fact that it is the electrostatic attraction that brings stellar cores to the sun is illustrated here. Basically, they have a positively charged inner core. They don't have a negative outer layer because they are depleted in electrons. So this positive core is attracted to the sun's outer negative layer. And the electrostatic attraction, which is illustrated by this orange arrow, is much larger than any gravitational attraction that the object may feel towards the sun, and this is because of its low energy status. Now, one of the details that has emerged from observing the stellar cores in the sun's corona is that stars and planets are very similar, and both are powered by radioactive decay or fission of heavy unstable nuclei in the solid dense cores, as this process releases photons which are absorbed by the particles in the core. This photon energy is then shared to all particles and will thus spread throughout the object. Now, as mentioned above, an object's gravitational influence is dependent on the photon energy in its particles. But since larger or more massive objects would necessarily have more particles, we actually need to use energy per unit mass, or energy density, in order to determine the actual size of an object's energy reservoir. Now, gravitational influence refers to the strength of the gravitational interaction an object is able to have, and it's given by G, which appears in Newton's universal law of gravitation. And you may look at Article 210 entitled Stellar Core Gravity, tidal, and G is not constant. And Newton's law is given by this equation, where here is the G. The G is usually called the gravitational constant, but as I mentioned before, it's not actually a constant because it's dependent on photon energy within the particles or the objects interacting. And the two objects that are interacting would have mass capital M and lowercase m, and r is the distance between them. So this means that G is dependent on the energy density of the two objects. However, when we apply this concept to the particles that an object is made of, in other words, protons and electrons, and since the electrons are much less massive, about 1,800 times less massive than the protons, we realize that electrons have a much higher energy density than protons, which suggests that electrons are the primary particle carriers of gravitational energy. To illustrate this, we will consider an object made out of 4 protons and 4 electrons. Each of the particles has the same amount of energy. So this is what's illustrated here. Protons and electrons have the same amount of energy, E naught, but the proton is much more massive than the electron. So the proton would have a mass that is 1,800 m when the electron has just mass m. Now, if we have an object that's made out of 4 protons and 4 electrons, and the masses and energy are given as shown here, then the object initially has a mass of 7,204 m and energy 8 E naught. We can then determine its energy density, which is a measure of its energy reservoir. And we can calculate that by taking the total energy, which is 8 E naught, dividing by the total mass, which is 7,204 m. And when we calculate that, we get 1.11 times 10 to the minus 3 E naught over m. So that means that on this scale, we would place it here. That will be about 1.1. Now, if the object loses 2 protons, then the energy goes down to 6 E naught, but the mass decreases to almost half, 3,604 m of what we had there. So when we calculate the energy density, we get 1.67 in terms of 1.1. So that means that the energy density of this object goes up when it loses 2 protons. But when it loses 2 electrons, it goes down, because now we end up with 7,202 m for the mass, and the energy is 6 E naught, like over there. When we calculate the energy density, we get 6 E naught over 7202 m, which is 0.83 instead of the 1.67. So that's what's shown here. So we can see that the energy reservoir goes down when the object loses electrons, but it actually goes up when it loses protons. So this means that an object, when it loses the protons, it loses mass, and its gravitational influence increases because the energy density goes up. But when it loses electrons, it mainly loses gravitational energy, and its gravitational influence decreases. Now, when stellar cores arrive at the sun, they will first draw a large number of electrons from the sun's corona, which transfers a large amount of gravitational energy density from the sun to the stellar core. So this is one of the primary ways that the stellar cores absorb energy from the sun. It also suggests that the electron is the particle which transfers gravitational energy from one point to another, and is therefore of primary importance to a further understanding of the dynamics of electrogravity. Now, electrons are also the particle responsible for electric currents in circuits, which suggests that electric currents do not just transfer electric energy, but also transfer gravitational energy. In conclusion, the electron seems to be of primary importance in the transfer of gravitational energy, and thus of primary importance in the understanding of electrogravity dynamics. One of the ways that the stellar cores draw energy from the sun is through drawing electrons from the sun to themselves. Now, we have the references here. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.